Please acknowledge on the chat if you are able to hear me clearly. I have seen a new student coming in today, Trishul. Welcome, Trishul. Shrijan. Shrijan is also a new student. Welcome, Shrijan. We have all our other students, Ananya, Aniket, Aryan, Diven, Rishik. Okay, Shrijan is okay, fine. Okay, Shrishti, welcome. So last time we had stopped at the Pascal's triangle. So we will start from there. Okay, just a quick recap of the Pascal's triangle. So this is how the Pascal's triangle is created. You can see that there is 1 and 1 initially. Okay, so you see that there is a 1 here, and then there is a 1 here, and there's another 1 here. However, this number, that is 2, is obtained by adding the 2 ones. Okay, so the number in the middle and in the next row is obtained by adding the previous 2 numbers. If you notice carefully, you will find that all these numbers are always going to be 1. So on the left extreme you will have 1. On the right extreme also you have 1. And then these numbers are obtained by simply adding these 2 numbers. Okay. So here arrow is shown. So 1 plus 3 will give you 4. 3 plus 3 is going to give you 6. 3 plus 1 is going to give you 4, and so on and so forth. Okay, so this is the construction of the Pascal's triangle. Now, this is one of the applications of Pascal's triangle. What you see on the screen is a basic expansion of a plus b the whole square. What you see here is a plus b the whole square. So a plus b the whole square we all know is a square plus 2ab plus b square. Okay. However, if you observe carefully, the coefficient of a square is 1. The coefficient of AB is 2, and the coefficient of B square is 1. So what you observe here is when I'm going to expand A plus B the whole square, I will get A square plus 2AB plus B square, but the coefficients 1, 2, 1 are nothing but the row of the Pascal's triangle. Okay, what you observe here is that the coefficients 1, 2, 1 are nothing but the rows of the Pascal's triangle. If you observe, the highest order in this case, that is the highest power in this case, is 2. You are expanding a plus b the whole square. Okay, so I will be taking this row which has 1, 2, 1. But if I was expanding something which had an order 3, then I would be taking 1, 3, 3, 1. That is the next row. The coefficients are going to be the numbers in the next row. That is 1, 3, 3, 1. This is one of the applications or linkages that one can make between the algebraic expansion and the Pascal's triangle. Let us look at another example. This time I will be taking the highest order as 3. I will be taking the highest order as 3. Okay, and that is the reason why I will be selecting this row of the Pascal's triangle, which is 1, 3, 3, 1. and this is what I will observe. I will also like to highlight one more important thing, which is if I have A and I have B which I need to expand, if I have A and if I have B that I have to expand, that means if I have to expand A plus B the whole cube, then what I will do is I'll simply write A, B, then I will write A, B, then again I will write A, B, then I will write A, B, okay. Then I'm going to add the coefficients, that is 1, 3, 3, 1, and look at the power is also in a sequence, okay. You observe that the power of A is descending from the highest order of 3 to 2 to 1 and then 0, and if you see the power of B, it is ascending from 0 to 1 to 2 and then 3. I hope that is clear to everybody. This is a higher order expansion of A plus B the whole cube. Okay, what I have simply done is I have taken the row 1, 3, 3, 1, used the coefficients, and then there is a pattern in the power also. The power of the first term of the expansion, that is A, is descending from 3 to 1, 0. This 3 is because this order is 3. So you start from 3 to 1, 0, and the power of B is going to be 0, 1, 2, 3. Okay. So it's written here that there is a pattern in the power of A and B as well. The power of A descends from 3 to 0, and the power of B ascends from 0 to 3. Okay, so what I will finally get after cleaning up and simplifying everything is A cube plus 3A square B plus 3A cube. This should be sorry about that. It should be, this should not be there. So it should be 3AB square plus B cube. So the final expansion of A plus B the whole cube is A cube plus 3A square B plus 3AB square plus B cube. Okay, that is going to be the final expansion of A plus B the whole cube. How would things change if there was A minus B the whole cube? What I simply do is use the same procedure, but I will alternate the plus and minus sign. So starting with plus, then minus, then plus, then minus. So if it is going to be A minus B the whole cube, it is going to be A cube minus 3A square B plus 3AB square plus B minus B cube. So A minus B the whole cube will be A cube plus 3A square B plus 3AB square minus B cube. Okay, is my voice is breaking? Okay, are the students able to hear me clearly? Okay, fine. Okay, so that was A plus B the whole cube, and if it is A minus B the whole cube, then you have A cube minus 3A square B plus 3AB square minus B cube. Okay, how would things change if it was A plus B raised to 4? For A plus B raised to 4, it is going to be A raised to 4 plus 4A cube B plus 6A square B square plus 4AB cube plus B raised to 4. Remember that the highest power here is 4, and that is the reason why I have selected this row of the Pascal's triangle. Similarly, if you observe here, if it is A minus B raised to 4, then what happens here is that the plus and minus alternate. So starting with plus, minus, plus, minus, plus. So any higher order powers, you can keep expanding in the same way. Okay, it is very simple. Pascal's triangle can be used for expansion for any what we call as the binomial expansion. For any binomial expansion, you can use the Pascal's triangle in order to do an expansion. Any higher order expansion you can do using this method. Okay. I have a request here, as Aryan is saying that he is not following what is happening. I don't understand. No problem, Aryan. I'll go back once again. It's a very simple thing. Okay. What we are trying to do here is we are trying to connect a Pascal's triangle with expansions. I'm very sure that you must be introduced to this expansion of what is called as a plus b the whole cube. You must have gone through this expansion before. You must be aware of this expansion a plus b the whole square. A plus b the whole square expansion is a square plus 2ab plus b square. Now what I'm trying to do is I'm trying to draw some linkages here. If you see, the coefficient of a square is 1, the coefficient of ab is 2, and the coefficient of b square is 1, and it is nothing but this row of the Pascal's triangle. See, if you see here clearly, the row has got numbers 1, 2 and 1, and that is what is the coefficient here, 1, 2, 1. So in fact what I'm trying to say is that a plus b the whole square has derived its coefficients from the Pascal's triangle 1, 2, 1. Similarly, if it was a plus b the whole cube, then the coefficients would have been 1, 3, 3, 1, and that is what you will observe in the next slide. Okay, so in the next slide you observe a plus b the whole cube is a cube plus a cube plus 3a square b plus 3ab square plus b cube. Okay. What I am also trying to say here is that there is a pattern for the power also. Look at the highest power is 3, and you see the power of a, it is descending from 3 to 2 to 1 to 0, and the power of b is ascending from 0 to 1 to 2 to 3. Okay, I hope that is clear, Aryan. Are you getting it now? Good, very good. He is getting it now. Very good. Similarly, what I simply wanted to say was that if the sign here is going to be a negative sign, then here it is going to alternate plus, minus, plus, minus, plus. So you are going to have alternate signs starting with plus. Always this is going to happen. And similarly, now a plus b raised to 5 is what you can expand using these as coefficients. A plus b raised to 6 you can expand using these as the coefficients. A plus b raised to 7 you can use, or you can expand using this as the coefficient. Every time the pattern for the power will remain the same. The power of a is going to descend from the highest power of 4. So 4, 3, 2, 1, 0, and remember you have to go up to 0. And the power of b is going to ascend starting from 0, then 1, 2, 3 and finally 4. Okay, I hope this is clear now. Does anyone have any doubts, or should I move ahead? Okay, I'll move ahead now. Now this binomial expansion that we just saw, which was a minus b the whole cube, which is a cube minus 3a square b plus 3ab square minus b cube. What I have simply done is I have rearranged this as n cube. I have rearranged this as n. So what I'm simply saying is n cube can be written as n minus 2 plus 2 the whole cube. Now what I'm trying to do is trying to bring about a linkage of what we had done last week on the cubes. Okay, and what you will observe is that when I'm going to expand the right hand side of n cube, which is n minus 2 plus 2 the whole cube, using the binomial expansion, I will get n minus 2 the whole cube plus 6, n minus 2 square plus 12, n minus 2 plus 8. And therefore what I observe here is n cube can be written as n minus 2 the whole cube, which is nothing but the general expression for 0 sides of the cube painted, plus 6 n minus 2 the whole square was nothing but the general expression for one side painted, 12 n minus 2 was general expression for two sides painted, and 8 was always the answer for all the three sides of the cube painted. So here is one more linkage that I am trying to draw between binomial expansion and what we saw of the painted cubes last week. All the expressions put together, so it's nothing but all the expressions of the cube can be summed together in one expression of a binomial expansion, which is n cube. Only thing is what I have done here is I have just rewritten it in a different way. N cube can be written as n minus 2 plus 2 the whole cube. N cube can be written as n minus 2 plus 2 the whole cube. So there are quite a lot of linkages that I'm trying to draw here. Okay. Look at the construction of the Pascal's triangle. In case of a Pascal's triangle, I once again observe carefully. What I will see here is Pascal's triangle. What I see here is that I have counting numbers. Sorry, I have all ones in this sequence. I have counting numbers in this sequence 1, 2, 3, 4, 5, 6, 7, 8, 9. These numbers are called as triangular numbers. Okay, so first we will understand what triangular numbers are, then we will just touch upon the idea of tetrahedral numbers, then pentatope numbers also. Okay, let us look at this interesting number sequence which is called as the triangular numbers. We know that counting numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are counting numbers. Counting numbers are an arithmetic sequence because what you observe here is that there is a common difference between these two numbers. 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1, 5 minus 4 is 1, and so on and so forth. If the first term is 1, the common difference is 1, un is equal to 1 plus n minus 1d. So the general expression for counting numbers is un is equal to n. This is the general expression for counting numbers. This is what we had seen even last week. Last week we had discussed we had discussed the arithmetic sequences, and counting number actually forms an arithmetic sequence. It has a common difference of 1. Okay, it has a common difference of 1. Its first term is also 1, and the general expression for counting numbers is un is equal to n. Let us look at another sequence, what is called as a triangular numbers. A triangular number or triangle number counts the objects that can form an equilateral triangle, as in the diagram on the right. So the triangular number sequence, which has numbers like 1, 3, 6, 10, 15, 21 are nothing but the sequence forming triangular numbers. Okay, there is a small question there answered already. How many dots will there be in the next triangle? In the next triangle there are going to be 28 such dots which will form equilateral triangle. So this number sequence that you see here, which is 1, 3, 6, 10, 15, 21, and then even 28 and so on and so forth, is what is called as the triangular number sequence. Okay. Now let us observe what is the nature of the triangular sequence. As we had discussed last time, what you see here is every time you are doing a common difference, in the first stage the difference is not common, but in the second stage the difference is common. Whenever the difference is common in the second stage, the general expression is a quadratic equation of the form an square plus bn plus c. Okay, how do I get the coefficients a, b and c? Just a little bit of recap. Last time we had discussed the common difference that you are getting in the second stage. You can say 2a is equal to 1. So the answer that you will get for the coefficient of a is going to be half. Now if a is half, I can also get the value of b, because I know that 3a plus b is equal to 2. So what I will get is the value of b. The value of b also turns out to be 0.5, and then I will be using this expression a plus b plus c is equal to 1, which will give me the value of c as 0, and then I'm going to simply substitute a as half, b as half, and this is going to be the general expression for any term in a triangular sequence. Okay, any term in the triangular sequence can be obtained using the formula half n plus 1. Is everyone following this? If there is any doubt, any questions you want to ask, this is something we had discussed last week. Last week we had discussed two sequences, arithmetic sequence and the quadratic equation sequence. Okay, I have these answers coming in here. People are saying that they are understanding, so great. Let me move ahead. Okay, here what I have done is I have simply done a trial of the formula, whether the formula is working or no. So when I'm going to substitute n as 1 in the formula, what I get is t1 is equal to half 1 plus 1, which is equal to 1. T2 is going to be half 2 plus 1, which is equal to 3. T7 is half 7 plus 1, which is equal to 28, and we saw previously that the seventh term of the triangular number is 28. Okay, if we go back again to the slide, okay, where I have seen all the triangular numbers. If you see the slide, look at the triangular number. First term is 3, first term is 1, second term is 3, and the seventh term is 28. Okay, so the general expression for a triangular number sequence is half n plus 1, and I have validated the result half n plus 1 using the formula and substituting it in the formula, substituting n in the formula. Half n is 1 plus 1, so what I get is 1, and so on and so forth. So the formula half n plus 1 works. Let us look at another type of sequence. This sequence is called as the tetrahedral number sequence. The tetrahedral number was the next column that you had seen on the diagonal column that you had seen on the Pascal's triangle, and the numbers involved 1, 4, 10, 20, 35, 56. And if I observe closely, see what you observe here. This number sequence that you have is nothing but the triangular number sequence. Only thing is, what is missing here is 1, because 1 is also a part of the triangular number. So from second term of the triangular number, you can see the triangular number sequence here. Okay, 3, 6, 10, 15, 21, 28 is a triangular number sequence. So I applied the same logic in order to get the number in the next stage. And the number in the next stage of a tetrahedral number sequence is going to be 84. Now, what I have done is simply put down the tetrahedral number sequence here. These are the number sequence of the triangular numbers. Then I went on to find out the common difference, but it was not common, but this number sequence was common. Since the number sequence was common in the third stage, the highest power of the general expression has to be a cube. I have derived this. For a forum like this is a little higher order idea. So I will not get into the details of how I got this general expression. But students who are curious, okay, the hint is here. If you are a curious student, then I expect that you can find out and unearth the common formula or the general formula for a tetrahedral sequence. Okay, the general formula for a tetrahedral sequence is n plus 1 n plus 2 divided by 6. Let us see the validity. Does it work? Yes, it is working. I got the first term as 1, and the first term of the tetrahedral sequence is 1. The second term is 4, and the seventh term we had derived in the previous slide, which was 84, and we are getting 84 here. Okay, but I will leave it upon the students to derive this. Okay, derive this general expression for a tetrahedral sequence. Pentatope numbers, that is a sequence of pentatope numbers 1, 5, 15, 35, 70, 126, 210. General expression for pentatope number is 1 upon 24 n plus 1 n plus 2 n plus 3. Look at this, there is a pattern in this. See, look, there is a pattern in this. It is n plus 1 n plus 2 n plus 3. Okay, if I connect this with the previous one, okay, what was the general expression I got? 1 upon 6 n plus 1 n plus 2 n plus 1 n plus 2. Okay, similarly, look at the one behind, that is the triangular number. It was half n plus 1. Okay, if you continue doing this, okay, continue exploring this, okay, you might be able to derive some sequence with subsequent numbers also, like say for example 1, 6, 25, 56, 126, 1, 7, 28, 84, 1, 8, 36, 1, 9, and so on and so forth. So there is some mystery behind these numbers. Okay, inquisitive students who would want to know more about this should try to find out what is the sequence, what is the relation between the coefficients. Okay, there will definitely be some kind of relation. I can see some pattern happening here, like say for example the coefficient in this case is half. Then when I go to the next one, I find that the coefficient is 1 upon 6. This coefficient is 1 upon 6. Then when I go to the next one, it becomes 1 upon 24, right? So there is some kind of I'm sorry, there is some kind of a sequence in the coefficients as well. But if I try to do that, that is going to be very lengthy and it will take a lot of time. There's a lot of discussion, so I will leave it upon the students to find out the mystery behind the coefficients. But definitely I can see some pattern here, I can see a pattern here which is n, n plus 1, n plus 2, n plus 3. I can see some pattern here also n, n plus 1, n plus 2. I can also see a pattern here which is n, n plus 1. I need to go back to the Aryan. Which slide do you want to see? S. Sorry, I'm not getting. Which slide do you want to see? Is the triangular number? This was the first sequence, counting number sequence, whose general expression is n. Then this is the triangular number sequence. This was the calculation. This was the calculation for the triangular number sequence. This calculation is what we had seen last week. This was the general expression that we had found out if there is a common difference in the second stage. If there is a common difference in the second stage, then this was the general expression that we had found. And then we also found out last time that we can simply use formulas like these. We can simply use formulas, that is, one is this one, 2a is equal to 1. Then we can use the formula 3a plus b is equal to 2, that is this 2 we are talking about. And then a plus b plus c is equal to 1. Okay, and this one that I see here is actually this one. The one that I see here is actually this one. So we have three formulas here. 2a is equal to this one, 3a plus b, which is equal to 2, and then we have a plus b plus c, which is equal to 1. So there are three main formulas that will help me get the coefficient values, which is a, b, and c. Once I have a, b, and c, okay, I can simply use that in the general expression. Since the value of a is half and the value of b is half, the value of c is 0. The general expression is half n, n plus 1. Same way, there is in the tetrahedral sequence also there is a similar kind of idea, but I get the common difference in the third stage. And because I'm getting a common difference in the third stage, the highest power of the general expression has to be a cube. But like how I had derived things last time, you need to derive this on your own and find the general expression, which will eventually simplify to this one. And same way, when I go to the pentatope numbers, the general expression turns out to be this. In the pentatope numbers, obviously the highest power or the highest order is 4, and therefore the common difference you are going to derive in the fourth stage. But it's a lengthy process, and I would leave it upon the class to work on this assignment. But it is really optional. I mean, unless you are really interested and a keen and inquisitive math student, I don't think you are going to get into this derivation of general expression. But if you do that, it is going to be a great exercise. Okay, so before I move to the next idea, okay, which is indices, we will take a short break here, and we will meet once again after the break. Welcome back, everyone. Yeah, thank you, Aryan. Okay, before we move on to the next topic, which is rules of indices, I have something to share with the entire group of students who have already taken the junior and senior contest couple of weeks ago. According to the information that we have received, we have found that the students have not performed well on the test, and that is not the kind of scores that we are expecting from students in Hyderabad. We have found that almost all the students have not done as expected, and therefore at Transitions Lab Prep School we have taken a decision that we will be offering the students a re-examination. We request all the students to get in touch with our Hyderabad office and we will arrange for a re-examination of the ASMA 1 junior as well as the senior contest. We expect students to come well prepared for these examinations. The scores that we have seen are not acceptable at all, especially when there is so much support that is there for the students. We really expect the students to do well, and so we have decided that the students will take a re-examination. The Hyderabad office will get in touch with you with the dates and schedules, etc., of when this re-examination is going to be held. And we expect that the students should come well prepared. In case the students are finding it difficult, then please get in touch with the Hyderabad office and find out how you can be helped. We have two people handling the office there, Pranati Patel and Niharika Tyagi. You can get in touch with any one of them and they will be able to guide you. If you need any support from us here, please get in touch with us. Please write to us so that we can help you score better. Please share your number, Pranati, if you are there, so that students can get in touch with you. You can share your email ID as well. You can see Pranati's number on the chat screen. Pranati will also write her email ID. And Pranati, you need to come up with a date when we will be holding a re-examination for ASMA junior as well as senior contest. Okay, we have that email ID coming up on the screen, support@transitionslab.com. Please find out from the students what the issues were, why was the performance not as expected, and we will definitely take it ahead and help the students score well on these examinations. Okay, let us continue with the class. On the screen, you observe rules of indices. For the students, I want to ask them, are you familiar with the rules of indices? Are the students attending this class familiar with rules of indices? Yes, Rishik says he is. Aryan says no. Srijan says yes. Trishul also yes. Okay, great. I think most students are aware of the rules of indices. For students who are not aware of these rules and for students who want to quickly recap, this alphabet that I see here, which I am now shading in yellow, this is called as the base and this number which I am now shading in yellow is called as the power. In rules of indices, the first rule is that if a raised to n is multiplied by a raised to n, then what you end up getting is a raised to m plus n, which means that the base remains as it is and the powers are added. What you see here is the powers are added. You end up getting m plus n. Similarly, if you have a raised to n bracket m, then what you get is a raised to m into n. A raised to m divided by a raised to n is a raised to m minus n. So remember, if it is multiplication, it is plus, and if it is division, it is minus. A base raised to the power of 0 is equal to 1. A base raised to the power of minus 1 is 1 upon a. A base raised to the power of minus m is going to be 1 upon a raised to m. A raised to half can be written as root a. A raised to 1 upon m can be written as mth root of a. A raised to n upon m, okay, this is n upon m, can also be written as a raised to 1 upon m into n, and therefore this is going to become mth root of a raised to n. The formulas are on the screen. The formulas are on the screen. Just quickly go through the formulas. Okay, just go through the formulas quickly. I'll pause for a minute. Just quickly go through the formula. Go through the formulas quickly. I'm pausing for a moment. If there is any doubt, please let me know. I have shown these rules as rule 1, first rule, second rule, third rule, fourth rule, fifth rule, and sixth rule. Let me know on the chat if there is any problem with any of the rules. Okay, great. So I will move to the next slide, which has got an example. The rule is on the screen once again, and the question is also on the screen. What you have to do simply is to simplify this expression. There are all the rules on the right hand side. Can students quickly work the answer and share it on the chat? Can students quickly work the answers and share it on the chat? The rules are on the right hand side. You simply have to use the rules to get the answer. Does anyone have the answer? Is anyone having the answer? No one yet? This question is based on the idea of rule number 2, and according to this rule, the power 3 is going to be applicable to every term inside the bracket. Every term inside the bracket is going to be raised to the power of 3. So 3 raised to 3 is 27. 2 multiplied by 3 is going to be 6. 4 raised to 3 is going to be 64. X cube raised to 3 is going to be x raised to 9. 2 raised to 3 is going to be 8. X square into 3 is going to be x raised to 6. Y cube raised to 3 is going to be y raised to 9. So what I have simply done is the power that is outside the bracket I have applied to every term inside the bracket in order to get that as the result. In the next step, what I'm going to do is I'm going to take all the numbers together and separate the variables. So 27 into 8 upon 64 are all the numbers, and the variable is y raised to 6, which comes from here, x raised to 6 that comes from here, y raised to 9 that comes from here, and there is x raised to 9 that comes here. Then I will simplify the number, that is 27 into 8 upon 64 is 27 upon 8. You need to add up all the powers. So 6 plus 6 plus 9. Okay, there is a small mistake here. The power should not be 15. This power should not be 15. The sum of 6 plus 6 plus 9 is 21, right? Thank you. So it should be 21. Oh no, I think I was right, sorry. Yeah, it is correct. See, 6 plus 9 is 15, so y raised to 15. And this variable is x raised to 6, and this is x raised to 9. So it is going to be x raised to 6 minus 9, which is x raised to minus 3. And because it's x raised to minus 3, I can use this rule. I can use this rule and I can get the x cube down. So your final answer is going to be this one, 27 upon 8 y raised to 15 upon x cube. So my final answer is 27 upon 8 y raised to 15 upon x cube. So in this one question, we are using several different ideas of indices to get the final answer. 27 upon 8 y raised to 15 divided by x cube. Let us look at another example. The formula will appear on the screen first, and this is the question. I am waiting for the answer. Let us see who answers this question first. Ananya has the answer there, but are you sure that is the answer, Ananya? Srijan also has an answer there. Anyone else who has the answer? I have Rishik also answering this question. Trishul has also answered. Let us check. First, what I have simply done is I have rearranged 9 raised to n as 3 square raised to n and 3 raised to n plus 2 as 3 raised to n into 3 square, and that I have divided by 3 raised to 3n. Okay, is everyone with me as far as the first step is concerned? The first student to answer this question correct is Rishik. Well done, Rishik. Okay, so what I've simply done is I have simply written this and rearranged, and then I have taken the number separately and the variable and the 3 raised to power of n separately. And then what I observe is that this 3 raised to 2n plus n minus 3n, this will give me 3 raised to 0. And 3 raised to 0, anything raised to 0 is always equal to 1 according to this rule. So what I end up getting is 1 into 9. So the answer is 9. Rishik was the first student to answer this question correctly and the only student who has answered this question correctly. Well done, Rishik. Let's move on to the next question. The formulas are appearing on the right hand side, and here's the question. Rishik has the answer again. Anyone else who wants to answer this question? It's based on the similar idea of what we had discussed earlier. Okay, this is how I will do the rearrangement. Okay, this is how I'm going to do the rearrangement. 3 raised to x, 3 raised to x into 3, 3 square divided by 3 raised to 2x. Then I will collate and take everything together. So if I do that, I will end up getting 3 raised to 2x divided by 3 raised to 2x. So these can be taken together. And then what I have here is 3 into 3 square, which is 27. So therefore, Rishik is right once again. Aryan has also answered the question correctly. So Aryan is the second student who has answered the question correctly. The answer to this question is 27. So once again, Rishik was the first student to answer the question correctly, followed by Aryan. So I'm happy students are getting the answers now. Is everyone else also getting the answer? Is everyone following the explanation? Is everyone also following the explanation? Good. Let's look at another question. The formulas are appearing on the right hand side, and this is the question. Let us see who answers this question correctly and first. Okay, Anket has the answer. Even Aryan has answered the question. Both Aniket and Aryan have answered the question. Trishul's answer has also, I can see it in the chat box now. Come on, others. No, please participate. Aniket, Aryan, Trishul have already answered the question. I'm waiting for others to participate. Come on, Rishik. Rishik, Shrijan. Okay, let's look at the explanation. So once again, I'm breaking it up. And then I'm separating the numbers with the power n and the constants. So a little bit of rearrangement will make it look like what you see on your screen now. And then that will get simplified to what you now see on your screen. And then from this step, you need to go to that step which is up there. So 2 raised to n minus 2 raised to n is going to give you 0. Then multiplied by 2 and 2 raised to 3n. When I solve this, I'm going to get 2 upon 2 raised to 3n. And therefore the final answer is going to be what you see on your screen. This is the final answer. 2 raised to 1 minus 3n. Because remember, 2 by itself means 2 raised to 1. A lot of students attempted the question, but none of them got it right. I hope the explanation will help you. Your final answer should be 2 raised to 1 minus 3n. That is the final answer. 2 raised to 1 minus 3n. Okay, that's another question appearing on the screen. That's another question appearing on the screen. Shrijan has the answer already. Aryan's answer has also come on the screen. Trishul's answer is also on the screen. Look at the steps now appearing on the screen. Okay, so none of the answers again were correct. The final answer to this question is 24 into 5 raised to n minus 1. The final answer was 24 into 5 raised to n minus 1. Is everyone at least getting the answer? After looking at the solution, are you getting it? No, Aryan, it won't be 120. You cannot multiply these two numbers. You cannot multiply 24 and 5. Your answer has to be written as 24 into 5 raised to n minus 1. Okay, it should not be 24 multiplied by 5. You cannot do that. You cannot multiply 24 and 5. Yeah, they are unlike terms. Shrijan is right. So you cannot multiply. Your final answer has to be what appears on the screen like this. You can write the multiplication sign if you want instead of the dot. That is all right. You can write a multiplication sign instead of the dot. But you can't multiply the two terms. This is another question appearing on the screen. That's one more question appearing on the screen. Aryan has an answer there. Shrijan also has an answer. Anyone else? Anyone else who has the answer? Okay, this is how I will break the terms up with the powers. Then I will take systematically, I am going to take the numbers separately and the numbers with the powers separately. And what I clearly observe here is I am left with 2 raised to n, which I can eliminate. Okay. So the next thing what I see here is sorry about that. What I see there is 16 minus 2 upon 2 into 2 cube, which can be simplified as 14 2 into 2 cube, which is nothing but 7 upon 8. So the final answer is going to be 7 upon 8. No one got that answer right, but I hope everyone is following the explanation. Okay, let's go to the last question of today's session. The formula appears, and that is the question. The problem is on the screen. Aryan has an answer there. Aryan already has an answer, but the answer is not correct, Aryan. So this is what is going to happen. On the right hand side, root of 3 can be written as 3 raised to half. I have used this rule. So what I get is root of 3 can be written as 3 raised to half. Then you will end up with 3 raised to x plus 1 is equal to 3 raised to 3 by 2, because you have to add the powers. So 1 plus half is 3 upon 2. And now when the bases are going to be the same, the powers can be equated. You can equate these two powers. So what you get is x plus 1 is equal to 3 upon 2, and therefore x is equal to half. So the final answer to this question is x is equal to half. I hope everybody got the concept of indices. Okay, good, Aryan, very good. So now I advise all the students to get in touch with Pranati. Pranati will get in touch with you all with the schedule of the examination, the re-examination of ASMA Junior and Senior contest. I expect students to do well this time. We are giving one more chance to the students. In case there is any help or support that is required from our side, please let Pranati know about it. So I will get the information. All the best to everyone. Thank you. Good night.